Hello, in this video, we will discuss about another category of the reactions of alcohol that in which alcohol behave as nucleophile and electrophile. Okay, as we know that alcohol are the compounds with the functional group OH, and since you have the lone pair of electron in the OH group of the alcohol, this lone pair of electron can behave as the nucleophile. Because of this lone pair, it can behave as the nucleophile. So whenever it behaves as a nucleophile, for example, it can react with, say, for example, alkyl halide to give the uh, SN substitution reaction. So this will attack on the R group and X will leave as the leaving group. So whenever it is behaving as that, in this case, it is behaving again. Alcohol is behaving as nucleophile. So whenever it behaves as a nucleophile, then what happens is the result is ROH is as it is here. Say this is R prime is attached. You see X is already leave as leaving group. And since now this oxygen has 3 bonds, that is when it will have plus. Now, in order to behave as a nucleophile, the next step that needs to happen is to deprotonate this hydrogen. So this X minus will grab this proton, deprotonate to neutralize this plus charge. So that is how you can see it is forming the ether. So whenever alcohol is acting as a nucleophile upon reacting with alkyl halide, it can result in the formation of ether as the product. This is the example to show alcohol acting as the nucleophile. Now, as we say here, alcohol also can act as the electrophile. So whenever the alcohol is acting as the electrophile, in this case, the carbon that is bearing the OS group, that carbon that bears the OS group, that is what will act as the electron loving center. This carbon will be the electrophilic center. But whenever it is acting as the electrophilic center, this OH will have to leave as the leaving group. But as we know that, so again, we are trying to discuss here the alcohol as electrophile, but whenever it is acting as the electrophile, the carbon that bears the OH group needs to act as the electrophilic center, and OH group should be acting as the leaving group. But as we know that OH is a poor leaving group. So the first step that we need to do here is to convert this OH, which is a poor leaving group, that we need to convert that into a, this needs to be converted into a good leaving group. Now, to convert that into good leaving group, as you have studied previously, one thing that we could do is you can react with some kind of proton, and water, this OS group will get protonated, and it can form water as a good leaving group. OH2 plus, that will be the good leaving group, and this carbon will act as the uh, can act as the electrophilic center, so that water can be leaving. Okay, so nucleophile can attack here and water is leaving. So that is the one category of the reaction it can happen. But this water here is an inorganic compound, so here we have better, we can make better leaving group than that of water. So that is when we use the tosyl uh, tosyl group, or we can react that with paratoluene sulfonic acid, or TSOH. Okay, that is what we can use in order to make that as a good leaving group here. So in this case, what we do is the alcohol here OH, we react with either TSOH, para-toluene sulfonic acid, or we can also use TSCl, or para-toluene sulfonyl chloride. Let us try to understand what is TSOH and what is TSCl. Okay, TSCl. TSOH, also called para-toluene sulfonic acid, and the structure looks like this one here. This is a benzene ring. Whenever we have a CS3 group, that is what we call toluene, and on the para position, on the just opposite side of CS3 group, this is the para position. That is where the sulfonic acid group is there, S double bond O, and OH. This is what is called sulfonic acid. And again, please try to remember the structure of sulfuric acid. This is how we normally write the sulfuric acid, H2SO4 sulfuric acid, but this is the sulfonic acid group, and here is the toluene group. That is where the para-toluene sulfonic acid. And shortcut, it is represented as TSOH, para-toluene sulfonic acid. Or we can also use TSCl, that is called para-toluene sulfonyl chloride. So which is very similar to sulfonic acid. Only the difference here is in TSCl you have, this is the benzene ring. When you have a CS3 group, that is toluene, and sulfonyl chloride has S double bond O, and instead of OH you have here Cl. This is called TSCl, para-toluene sulfonyl chloride, and this is much better than TSOH in order to tosylate it. So the question is, how does this alcohol react with TSOH or TSCl to give the better leaving group? So basically what happens is, if we are using TSOH, then here water molecule will be removed, and the result here is the oxygen will be bonded with OTS, this toluene sulfonyl group. That will be a fantastic, excellent leaving group, much better than that of water. So whenever we are using TSCl, we are removing HCl as the side product, and OTS group is attached. If we are using TSOS, and water will be removed and OTS group is attached. So let's try to see the mechanism. How does that happen here? Okay. So whenever we are using some type of alcohol, say for example ROH, this is the alcohol, and these are the lone pair of electron. We are reacting with TSCl, okay, para-toluene sulfonyl chloride. And this lone pair of electron will attack on sulfur, and since there is a leaving group chlorine, this leaving group chlorine will leave, and the result here is ROH is already there, so it is plus. Now this will be attached with sulfur, and you have double bond O, and then we have here toluene group. And now next we deprotonate that. So this is again in shortcut, this is the group that we write as TS. Okay, so that is how you can, now you deprotonate this, then you can use any base to deprotonate that. It's a pyridine normally we use. Then the result is ROS double bond O, and then you have this whole toluene group is there. So this is the group that is again represented as TS. In shortcut, this one we write as ROTS. And this is the fantastic leaving group. And once we have this kind of leaving group there, you can do varieties of reaction, either substitution reaction or elimination reaction. Substitution elimination you can do using uh, tosyl group as the leaving group. So basically, say for example, you have, let's go to our original work here. You have OH, this is the alcohol. You can say primary, secondary, or secondary or tertiary alcohol. Now, whenever you react with either TSCl better, okay, again, remember the structure of TSCl, or you can use even TSOH also you can use. And when you use TSCl, what will be removed here? HCl is the one that will go away. The result here is carbon with C, okay, you have your H and your O. Now you have TS. This is excellent leaving group. Now, once you have this excellent leaving group there with this tosylated product, either you can do substitution reaction. You can react with any nucleophile, say for example OH or C and any nucleophile, and that will attack on carbon, leaving group will leave, and then you can have the uh, nucleophilic substitution reaction. See, the OS group now replaced by the nucleophile. Or since if you have the hydrogen and the beta carbon, again this is the alpha because there is a leaving group, this is the beta, and you can do, this is the substitution reaction. You have studied that in your Orgo 1. Substitution reaction can give the varieties of substitution product, or you can use some type of base to do the elimination reaction. Base will grab the hydrogen, will give you the double bond, and the leaving group will leave, and the result here is you have carbon-carbon double bond. That is when you will have the alkene as the product by the elimination reaction. The thing is, we are making OTS um, as the leaving group and can do varieties of reaction with that. So that is how the alcohol can act as the um, nucleophile or electrophile and can give varieties of reaction there. Now the next category of the reaction here that we wanted to discuss about the alcohol is the conversion of alcohol, conversion to halide. Alcohol can be converted into halides. That means here ROH, this is the alcohol, you wanted to convert that into RBr. For this, the best reagent that if you wanted to put bromine, memorize one reagent that is called phosphorus tribromide, PbR3, that will convert into RBr. Okay, so PbR3 will convert that into RBr. And if you wanted to convert into chloride, then you might think that, well, we can use PCl3, then you will get RCl, which is fine, but there is much better reagent than that. Okay, to convert into chloride, there is one very nice reagent. I strongly recommend you to memorize this. Memorize this one. Very good one is called SOCl2. That is what we call thionyl chloride. Thionyl chloride. Remember that. SOS. Whenever there is sulfur, we call thionyl chloride. That will very nicely will convert into RCl, alkyl halide with the chloride. But be careful for bromide. You don't have like SOBr2. We don't have this one, so you cannot use that. Only thionyl chloride for chloride, chlorine only. Okay, so this is the best reagent. But however, one precautions that you need to take is thionyl chloride are somewhat carcinogenic, that can cause cancer, so you need to be very careful while using this one. And there is one what we call is the Lucas reagent also.